Now let's look at scale and how scale impacts things, right? We'll look at vertical versus horizontal scale. Vertical scale, everyone is most familiar, right? In today's world, it's not unusual to have like a 10 terabyte disk with 256 gigs memory in a single machine, right? And from the data that we have, we see that but for like a very short number of, use cases that requires petabytes of data, most of the data fits in within a few terabytes or a few hundred gigabytes, right? So for most of the use cases, your data will fit on one machine. It is perfectly viable to say that my database is just one machine. However, machines go down, right? You can't predict, especially in today's cloud infrastructure, you don't have control, you don't run your DCs, you don't have any control over the machines, so machines go down. And in some cases, data has grown to like exabytes and petabytes. And who knows, I mean, you might be running a startup that today is only doing a few hundred gigabytes, which tomorrow could scale overnight, and suddenly you're looking at like a petabyte scale, right? Just to give you some numbers, let's say you grew to something like 10 million DAUs, daily active users. Doing some simple math, over 3 years, if you just had 10 million DAUs over 3 years without any growth, you would be looking at 36 petabytes of data, which is naturally not going to fit on 1 or 2 machines. So horizontal scale becomes inevitable. Now imagine I have to do concurrent operations, and I have to do these concurrent operations on a horizontal scale, which means that the previous lock that I was obtaining to maintain integrity, that lock I now have to obtain not over just one record on one machine, but on multiple copies of that record on multiple machines, right? And previously, what we had was that we had the index lookup happening only on one machine, where you would look at the pointer location in the memory, and the offset would point to the data element on to the data record on that disk. Now, however, you have an additional hop or an additional logic required to figure out, oh, I have this cluster of 100 machines. Where on these 100 machines is my data, right? You have that complexity as well. So this essentially is what I kind of commonly refer to as database hell. When you have to handle concurrent operations at this enormous scale, you come to what I would characterize as a database hell. So obviously we don't want to be in this hell, right? You want to minimize the hellish aspects of database. Sorry, did someone have a question?
Oh, no, sorry. I was just...
Okay, all right, cool. So how do we minimize database hell? We figure out what to reduce, right? And between reads and writes, what is extremely difficult to scale, as we saw, it is obviously the writes, okay? So one radical concept could be, what the hell, I will just not scale writes. And somebody would say, oh, well, why not? Right? So for most applications, the read to write ratio is something like 7:3 or 8:2 or 9:1. There are some exceptions, like if you have continuous data coming from IoT devices, or if you have an application like Uber, where there are constant driver updates, or you're in a multiplayer gaming like scenario, I mean, though we could argue that a peer-to-peer architecture could eliminate the need for multiple writes on a DB, but I mean, this is like a common write-heavy scenario, right? But for these exceptions, we figure out how to scale only reads, and we just do not scale writes at all. That's a perfectly viable option, because your reads are going anywhere from 100K RPS to like a million RPS, and this is typical of almost all large scale use cases, right? So how do we do this? From the single machine where, let's say, I'm taking the writes, I will just spawn multiple copies, commonly known as read replicas. So I'll spawn multiple copies, which means that each copy server can now handle a specific set of reads. So I could apply some logic where I can say that from the write machine, I will make a copy of records 1 to 1000 to machine 1, make a copy of records 1000 to 10,000 to machine 2, copy of records 10,000 to, I don't know, a million to machine 3, like some simple logic like that, right? And then all I need to do is on whenever I get a read for the record 10,000, I should just have the intelligence to go to machine 3 where it is located. Okay, some simple logic like this works. So this is a compromise, obviously, right? This compromise is important because we can't forget concurrency, and concurrency comes into play when you have to scale writes, correct? For consistent reads, let's say I have to make my reads consistent, as seen in the last example. The latency will now become a function of all the copying that I have to do, correct? So if I write a record and then I immediately send an acknowledgement that this record is written and forget about, I'll take care of the copying later, I will end up with inconsistent reads, like how we saw in the previous slides. So if I need consistent reads, I will have enormous latency, because my latency is now a function of waiting for all the copies to be successful. Only then the acknowledgement can go back, right? Whereas if I say I don't want consistent reads, my latency will be very fast. It is just a function of one write, and all the copies will be asynchronous. I don't have to wait until the copying is done. And hence you do this compromise, and this is what you commonly come to understand as strong consistency versus weak consistency in databases. And many databases, including Cassandra, allow you to tune this consistency level to say that I'm okay, I want low latency, weak, inconsistent reads, I'm okay with that, and the database will offer you that functionality. Or you can say, I'm not okay with this, I want strongly consistent, very consistent reads at the expense of a higher latency, and the database will allow you to do that. Okay, so you have to figure out what is a compromise that you need.